All right, let's try this again. What I'm going to do this time is I'm just going to talk through these notes that you already have and we have the videos for, but I'm just going to talk through them and see if that is going to help here. And then we can talk more about it in class. So we'll take our time in class on Tuesday and talk a little bit about this. But I wanted to at least talk it through with you just a little bit here so that we can make sure that we're on board. So, kind of what the dispersion is, as you can read, it's the degree which the data are spread out. So the bigger the dispersion, right, the bigger the standard deviation is going to be. For this particular problem, you can see that there is a lower limit of 55. So then that tells me that 55 is your bottom spot there. And with the class with the 15, so you're going here at 15. And then with this data, you're pulling out that your mean score is 100. So now you have these two pieces of data. This dispersion is greater because it's more spread out. This dispersion for University B is much smaller because it's really close together. That's what that's talking about. That's dispersion. How far apart is my data spread out? Check. The range is going to be my largest data value minus the smaller data value. So the biggest number we have minus the smaller number that's even possible. And like this data where it's these scores, we just keep using the same data. Then you can get the high score, which is 94, minus the low score of 62. So this has a range of 32. So whenever I post your scores, I'm going to give the range of 94 to 62 or whatever your scores are for your tests. I'm not going to do the subtraction, but I'm just going to give you the range of those values. So dispersion, how spread out is your data, the range, large minus small. We got this. Now, the deviation is the key here. So your standard deviation is based on the deviation about the mean. How far away from the mean is this? So the larger the standard deviation, the more dispersion that you have. Now the population standard deviation and the sample standard deviation, here are the formulas that go with that. I don't really care if you know that because we're not going to use those formulas. It's just nice to have that. What I want you to know is that the population is sigma, lowercase sigma, and the sample standard deviation is this S. And what you're going to do is actually plug that into your calculator. Excuse me, you can see that on the other video I did. I showed exactly how to plug into your calculator, and then you can get that figured out. So you put your data in your list 1, you hit second stat, and then you do the one variable statistics. So what you need to know is how to get this one var statistics on your calculators. If you're using the blue and white ones, then it does not show you variance, but that's no big deal. You just take your sigma that it is shown on there, right? That gives you that value. That's the hard thing to find. That's where this freaky deaky formula comes in. That is truly super cumbersome. If you're super interested in this, just go to the study plan and watch the videos on how to find it by hand. We're not going to do that. It's a huge waste of time whenever you have this awesome technology that'll do it for you because there's really no redeeming quality in finding it by hand. So we're going with that. And then once you get your standard deviation, just square it. And that's how you get your variance. That's it. So you plug into your calculator, you get your list here, you plug that into your calculator because this is the sample. We're going to focus on the sample that comes out of your one variable statistics. You square that and you get your variance. Now we'll talk more about variance later in the course and the value associated with it. But for now, we're going to use technology to come up with your standard deviation. And standard deviation is just how far away you are from your mean. And you're going to do the exact same thing. Now, for this one, you have those 100 pieces of data in University A and University B. You are welcome to plug all of those into your calculator, and then you can come up with this sample standard deviation and the sample standard deviation. The key to this one is the fact that we already knew the standard deviation was going to be bigger for University A, even though the mean is the same, because as we saw back here, this data is more spread out, therefore you have a larger standard deviation, meaning that it's farther away from the mean. Here, it's a much tighter graph that you're looking at, so it looks kind of like this, where this standard deviation, it spreads out that curve where your smaller and tighter data, it's that tight curve that you're looking at there. So the standard deviation is much smaller. And so this is kind of just a way to show you, oh yeah, so if we see the graphs of those two, we know that this graph is nice and tight, where this graph is much more spread out. That's what that means. Distance away from the mean. So one standard deviation is farther away because my data is more spread out. This is a much tighter standard deviation because my data is close together. That's what that is. Now, when you have to know your empirical rule. When you have a bell-shaped curve, it's just a standard where the majority of this is going to work out in terms of having this bell-shaped curve. If you do not have a bell-shaped curve, you cannot use the empirical rule. It just works with your bell-shaped curve, right? This rough bell-shaped curve that we're looking at, such as in University A. So we saw that with the graph. You make your bell-shaped curve. Well, you start with your mean in the middle. That's what that mu is, right? Or your S. Either way, it doesn't matter. This just means mean, and then this is your standard deviation. Whether you're talking about your population or your sample is irrelevant. The concept is still the same. Put your mean in the middle. Add a standard deviation every single time out, right? So 100 plus 16.1. This tells you your data values, and in this instance, we're talking about IQ. So then your mean is 100 points of IQ. The next standard deviation would be 116.1, etc. And so far up and down. You have to be able to draw one of these. That's the key to this. Know how to draw one of these. It is better for you if you know these percentages, because then you can add those up and work with it. The majority of your data is within that one standard deviation of 68%. 68% of your data is within one standard deviation. Then you spread it out within two standard deviations. Excuse me, you have 95% of your data. And then it goes from there. Notice the hill is right here, so this means most, right? In that middle. Then I've got a little bit more, and then it gets less and less as you go out. So knowing this empirical rule is going to be really helpful anytime you have that set up. Then you just look at once you have your bar graph, and then you just look at it, okay? 3 standard deviations, and you come out here to 3 standard deviations. We know that that is 99.7% of the data. Determined between 67.8 and 132.2, well, that is 2 standard deviations. So that's 95% of the data. To get part C, to figure out the actual amount, you have to go back to your data and literally count it up. When you literally count it up, you'll see that there are 96 of those scores. And so 96%, and we have 95% here. So our empirical rule is a really good indication. If you have bell curve, it's a good, without having to go through and count up your data. I mean, this data is enough. It's to have 100 pieces of data. But this way, you don't have to go back and count that. Your empirical rule is going to give you a really good, fairly accurate indication of what that is, which is nice. And then once you have your bell curve, then you just go through and you add it up. So above 132, so you add these two pieces. 2.3%, 0.15% gives me a total of 2.5%. So that tells me above 132.2 are the elite, if you will. There's only 2.5% of students that fall into that category. And that is helpful to make, scholarships and set up what they can expect from students, etc. All right, pretty cool. Now, if you have a bell curve, the empirical rule is the way to go. If you have anything else, you can look at Chebyshev's inequality. Where this works, the empirical rule holds only if the distribution is bell-shaped. Chebyshev holds regardless of the shape that you're looking at. So you can use the same data that we just did in that last example. It's nice to look at the comparison between empirical rule and Chebyshev. That's why we're doing this. So if you look at this within 3 standard deviations, Chebyshev is going to give you an 88.9. However, we know, and if we were to count up the data, then it's going to be closer within 3 standard deviations of the 99.7. So Chebyshev, especially in the bell-shaped curve, is going to kind of hit the low mark. It's going to be a little more conservative of what it is. Same thing we're finding here. Within 2 standard deviations is 75%. We know the actual is 96 because that's what we determined in that last example, right? So Chevy Chev here is much more conservative. It's much, it's not, because this is a bell-shaped, your empirical rule is much more accurate, is what it is. And so, but the thing is an empirical rule does require a bell shape to give that more precise result. So that's kind of the main thing here. We're going to talk in class on Tuesday about, give another, basically what I just said, a brief of empirical rule, because you need to know that, and making sure you know how to put standard deviation into your calculator. Beyond that, I would take a look at the information on that. Just look through it, those other videos, even though they don't have any sound, but it gives you an idea and it kind of breaks that down. You can follow along with it and get a good idea. I literally show you how to plug this into your calculator on that, so you'll be able to see what that looks like. All right, cool. Hopefully this will give us our nice Cliff Note version there. Our 3.3 notes is simply a weighted mean. Follow the formula. If you're looking at this, you've got 4 points for an A in a 4-hour class. 4 points for an A, 4-hour class. 3 points for a B in a 3-hour class, right? And then you just multiply those together, add them up, divide them by the total, and you get your GPA. So that's just weighted mean, is the sum of these two multiplied together divided by the sum of that weight. And that weight here in GPA is your hours, credit hours. All right? Awesome. I'll see you guys in class on Tuesday.